It's time for us to enlarge our chemical toolkit and find some chemical properties which will provide even more conversion relationships. The first one we'll look at is density. Density is a material-dependent property and a derived unit that links mass and volume units. If we know the mass of matter, we can use the density to tell us the volume of the matter. And naturally, the conversion works the other direction too. If we know the volume and the density of the matter, we can calculate the mass. On a solution map, if we ever need a link between the volume and the mass of a substance, what we are saying is that we need the density of that particular piece of matter, our volume-mass connector.
Density is the mass of a substance divided by the volume it occupies. Measuring density is a straightforward affair. First, we weigh the substance on a good calibrated scale or balance to obtain its mass. In the example shown, the metal machined nut has a mass of 308 grams. Note that this quantity has 3 sig figs. We now need the volume of the substance. The volume can be obtained by filling a graduated cylinder with a liquid that is less dense than the piece of matter we're measuring. If the nut were as dense as or less dense than the liquid, it would float in the solution and part of the nut would be above the liquid, and we don't want that. Our nut needs to be fully submerged in the liquid to get an accurate reading of its volume. Reading the bottom of the meniscus, it looks like we have 150 milliliters of liquid in the graduated cylinder before putting in the nut. We can only measure to the nearest milliliter with this graduated cylinder, so our measured value has only 3 sig figs. We then place the nut into the graduated cylinder and remeasure the liquid level. We will call this value 190 milliliters. To calculate the density, we divide the mass of the nut, 308 grams, by the volume of the liquid that was displaced when the nut was placed in the graduated cylinder. In this case, the volume of the nut is 190 milliliters minus 150 milliliters, which is 40 milliliters. Notice how the units are now in the ratio we desire for density, grams divided by milliliters. Being careful to keep track of the sig figs in this mixed computation, we end up with a 2 sig fig value of 7.7 grams per milliliter for the density of the metal nut. Now let's talk about the units of density. The derived units of density in base SI units would be kilograms per meter cubed, since kilograms and meters are the most fundamental SI units. That being said, it's more common to find tables of densities in grams per milliliter. It's rather straightforward to convert between the two unit sets. For example, if we have a density of 4,537 kilograms per meter cubed, we could convert kilograms to grams and then meters cubed to liters and then to milliliters, giving us a density of 4.537 grams per milliliter. You can see that this is equivalent to the simple relationship that 1 gram per milliliter equals 1,000 kilograms per meter cubed. Now, armed with this relationship, we can do the same conversion from kilograms meter cubed to grams per milliliter in one simple step. In measuring densities, we also need to note at what temperature we conducted the measurement. The mass of substances don't change with temperature, but the volumes they occupy will change. Most of the time when we heat something up, the volume increases, so the density of the material decreases upon heating, since we're dividing our same mass by a larger volume. The lesson here is that when we measure density, the value doesn't mean anything unless we also note the temperature at which the experiment was conducted. Let's do something with the density. Can we identify the metal that our nut was made from using density? Well, to answer that question, we need to measure the density of a wide variety of known substances and identify which ones have densities similar to the nut. On this slide is a very large table of densities for a variety of materials. Again, note that the temperature is also identified. Now, if we look carefully at the metals section of the table, we find that the density of a material that is similar to our experimental value of 7.7 grams per milliliter is steel. Well, that makes sense. Machine nuts are often made from steel, so a density measurement is a rather simple way to determine the possible type of material of an unknown substance, though not a definitive measurement. Bronze, lead, and iron also have similar densities to steel and also could be used to make nuts. So we would need other tests and measurements to be sure. Now, many times, especially for liquids and gases, we might find a list of specific gravities rather than densities. Specific gravity is simply a ratio of the density of the substance divided by the density of a reference material at a set temperature. The units cancel in ratios like this, so a specific gravity has no units. It's a comparison value and not a direct measurement. For liquids, a reference substance is usually water at 4 degrees Celsius, and for gases, air at 20 degrees Celsius and 1 atmosphere. Looking at the table, you see that a density of water at 4 degrees Celsius is equal to 1.000 grams per milliliter, so the magnitude of the specific gravities would be very similar to the actual densities for liquids, well, at least at 4 degrees Celsius anyway. Armed with this new bit of science, let's see what we can do with it. We need to state again what density represents and what it can do for us as we make connections in our solution paths. It links mass and volume units for specific substances. So let's do some problems. 4.3256897 grams of gold is how many milliliters of gold? Well, this is an easy single-step computation which needs only one connecting piece of information, the mass-volume relationship for gold, which is the density of gold. From the table, we find that gold has a density of 19.320 grams per milliliter. Gold is one of the densest metals on the planet. To put this in perspective, 1 milliliter of gold weighs 19 times more than 1 milliliter of water, which weighs about 1 gram. So we would expect for this mass of gold a result less than 1 milliliter. Density is substance dependent, so to be rigorous, we need to carry the word or symbol for gold, AU, as if it's part of the unit in the ratios. We also have to be aware that the density of gold is a measured value, and in this problem, the density value will be the quantity with the least number of sig figs in the computation. And sure enough, the value we obtain is less than 1 milliliter. Now we know that the price of metal, such as gold, is also a derived unit and becomes a relationship linking mass to money. The only problem with this derived unit is that it's a variable quantity that changes daily. Let's do a problem using both the price of gold and its density. 4.0 grams of gold is worth how many dollars? Well, looking at the stock market, we find that 1 gram of gold fetches $35.83. Not bad. Now, if we have 4 grams of gold, which we found in the previous problem has less volume than a penny, and work the problem, we have about $140 in our pocket. Wow, that's cool. Now let's do a few more problems. Multi-step conversions are demonstrated in the next 2 examples. 5.8 liters of iron weighs how many pounds? Our solution map will be liters to milliliters, then to grams via the density value of iron, and then eventually to pounds, resulting in a final value of 100 pounds, which should be expressed in scientific notation with 2 sig figs. And here is a multi-step conversion that also requires us to utilize density in our volume length derived unit too. 6.0 feet cubed of iron is how many pounds of iron? Look carefully at this important example and work it through. Instead of putting in an extra step in the solution path for 1 centimeter cubed equals 1 milliliter, I just assumed we knew this and skipped that particular step. Well, I was running out of room on the slide too.
Hopefully you can see how useful a density is to chemists. Again, remember, if you need a connection between volume and mass of a substance, you need to find its density. Catch you later.